Now let's hear from Gen Chiaki on a triggered star formation by population 3-star supernovae. Take it away, please.
Okay, can you hear me? Good. Okay, so thank you for organizing this conference, Anna, and thank you for giving me the chance to talk today. Okay, so today I talk about the triggered star formation by POP3 supernovae. I'm Gen Chiaki in Georgia Tech, and my collaborator is John Weiss, Corey Brammer-Smith in Georgia Tech and Italian groups. Okay, so my research interest is to study the transition from POP3 to POP2 stars. POP3 stars form in mini halo with masses of 10 to 5 to 10 to 6 solar masses, and it can explode as supernovae and enrich the interstellar medium with metals and dust. Then in this enriched cloud, POP2 stars form. I want to study this process of enrichment. Okay, in previous study, I studied about the single enrichment event. So that means the enrichment from a single POP3 supernova with different types of supernovae, normal quark collapse supernova and faint supernovae with different progenitor masses. In this case, I focused on the single enrichment, so the box size was small, 300 co-moving kilo/6. Then this result is press released on Texas University computing system. I really appreciate about this offer. And I can compare my results with the elemental abundances of observed EMP stars. The large symbols show my numerical result. It is the elemental abundances of enriched clouds, and the small dots show the distribution of observed EMP stars. For normal quark collapse supernova case, it's a black square. We can see the elemental abundances is the mass range consistent with the range of the elemental abundances of observed carbon normal stars. This indicates that the single enrichment is enough to explain the formation of carbon normal stars. On the other hand, for the faint supernova models, the elemental abundances is less than the observed carbon-enhanced stars, such as Keller star, by several orders of magnitude. This indicates that the multi-enrichment events are required to explain the formation of carbon-enhanced stars. The opposite result is shown in the semi-analytical studies of Tillman Hartwig, 2018. So they predicted the carbon-enhanced stars are likely to form in mono-enriched region, whereas the carbon normal stars are likely to form in the multi-enriched clouds. To clarify this, I ran simulation in the larger box size, 1 megaparsec. And today I show you the result of my test simulation, so with low resolution. But I expect that the result should be essentially the same as the higher resolution study. So I use the AMR code ENSO, and I use the chemistry and cooling library Glaco to solve the non-equilibrium chemistry for 48 chemical species, and I solved the 100 chemical reactions. Okay, so to study the multi-enrichment, I discretized the mass spectrum of population 3 stars into 6 mass bins. So in the intermediate mass regime, I assume that POP3 star explodes as faint supernovae, and the high mass regime, it explodes as a pair instability supernova. So again, to reduce the numerical cost, I discretize the mass spectrum. So it's not that for example, the 33 solar mass and 65 solar mass stars explode, yield the same metal mass and amount of each element. Okay, this is the result of my simulation. So as the redshift decreases, the interstellar medium is enriched with metals and dust. I show the metallicity and dust to gas mass ratio. It increases around the supernovae. Okay, and other redshift for 17, this contour shows the metallicity, and the different color shows a different mass being. So in this most massive halo with 10 to 7 solar mass, the POP2 stars form, and the 3 POP3 supernovae contribute to the enrichment disk cloud. So we can see the radial profile of metallicities from 10 solar mass faint supernovae and 33 and 65 faint supernovae. So 10 solar mass star can contribute to around 5 times 10 to minus 6 solar metallicity, and the other ones contribute around 10 to minus 3 solar metallicities. So interestingly, the elemental abundances of this cloud is very similar to the one of Keller star. So multi-enrichment is required to explain the formation of carbon-enhanced stars. And also interesting is this cloud can be plotted in the mono-enriched region, even though it is the multi-enriched. So yeah, it is a very interesting result. Okay, let me summarize my study. So I run simulations with large volume, 1 mega per sec. And so I can see the POP2 star formation in multi-enriched region. And next step is to run higher resolution simulation and to enlarge my simulation time to get the statistical samples of POP2 stars to compare with the large samples of observed EMP stars. Thank you so much.
Thank you very much. Thank you for so strictly sticking to your time limit as well. We have a first few questions on the Slack. For example, one by Tillman. Is it you or the simulation who decide how many supernovae explode in one halo? So I guess that's the setup.
Okay, so now I assume the one single POP3 star in mini halo. But yeah, it is there is a room to improve this point. Yeah, thank you so much.
Mm-hmm. And then Rafael is asking, would you also like to focus on pair instability supernovae since they contribute maximum towards gas enrichment in nearby regions?
Okay, so in this case, I impose some random sampling for POP3 stellar mass with some log flat IMF. So this is I have only the 10 POP3 stars. So then the massive star that explode as pair instability is very rare. But if I extend the time of the simulation, I can see the pair instability supernova explosion, and then these explosive explosion can enrich the very nearby halos. So then, it is very interesting stuff.
Mm-hmm. And we have a further question from Mattis. Very nice talk, Jen. When you say yeah, I agree. When you say the abundances are similar to the Keller star, are you referring only to the carbon and iron or all the elements?
Okay, I also follow all species from lithium to germanium, but I now show only the carbon and oxygen. And also in this talk, I show the magnesium to carbon ratio to compare to the Tillman's work. But I can follow all elements.
Okay, that sounds great.